right, thanks so much for coming. Thanks for this great introduction, but let's do it systematically, okay? That's my family. When I told Laura, who you see in the middle, that I got this phone call from Judy, she said, oh, we have a big problem. And I thought she's nixing the idea of my coming here. She said, you may have to buy a button-down shirt and wear it, too. So this is it. You're looking at it. I owe her big. Okay? The fellows in whose company I spent this year are truly amazing. I really don't think I've ever been in the company, such a rarefied company. So that's really quite an honor. And of course, all of this mountain of applications that we created, somebody had to read that stuff. And such a valiant act of selflessness cannot go unrecognized. So I really thank Liz, Judy, and everybody at Radcliffe for making such a great place to work. Similarly, in the Center for the Environment, the two co-directors made me at home pretty much from the beginning. And finally, my collaborators at the Chan School of Public Health. So I really thank all of them and you for coming, and let's get going. Oh, sorry. Once I hit the deck, I got acquainted with these two Harvard College pals, and we meet once a week. They tell me what needs to be done, then they tell me how they are doing it, and then we meet the following week and they show me how it was done. So, I mean, I taught at the University of Chicago for almost a decade. I've never seen anything like these two, so I feel very fortunate. Okay, so the plan for today is as follows. I'll start by introducing the problem heuristically, the problem that I'm interested in. I'll highlight some geophysical and societal costs of agriculture that motivate this work. Then I'll take you on a short personal aside that kind of augments a little bit the story that Judy told a few minutes ago, and then I'll share key results that will be the crux of the talk, and some concluding musings, and then it'll be your turn. Okay? So that's the idea. Now, what is rethinking the American diet? So here are two meals that I would be likely to eat, you know, kind of betraying my Middle Eastern origin. And here is something a bit more, let's say, American or European. The essence of my work and the essence of the talk that I prepared today is to show you how, if you know it or you don't, when you make a choice between one of those meals or between any two competing ingredients or any two competing meals, you're making really a whole cascade of important choices that you may or may not be aware of. So, for example, in that choice, you determine very much the nature of rural communities, how they are structured, how densely populated they are, etc. You certainly those choices have a lot to say about greenhouse gas emissions that are done on your behalf. And you also get to take sides in things that we don't often think about. That are kind of like societal strifes. So here's an example. This article discusses this long picket line that farmers in the Klamath Basin in Oregon formed because for the first time they were told that the US is actually going to honor its treaty with the Klamath tribe and share the water between alfalfa growers who got 100% of the water up until now, and the Klamath tribe, and they didn't like it one bit. You also get to make important contributions, large or small, to water pollution on land, okay, like creeks, ponds, even as far up as the Great Lakes. Lake Erie, every 10 years it seems that Lake Erie's obituary appears in the New York Times, and then it comes back to life ever so fleetingly. That has a lot to do with choices such as choosing between either of these or this. And it has a coastal oceanic counterpart, which seems a lot more devastating. But it happens with great regularity. Every summer, the entire northern part of the Gulf of Mexico is dead to the world. But dead, I mean literally dead, like that dead. And that is because of dietary choices, as I'll describe later. And finally, you also get to decide if by the time you're 82, you're going to be able, like this pal right here at 82, to ride across Canada from Nova Scotia to British Columbia, or you'll be, you know, warming the rocking chair on the porch. Those alternatives also have a lot to do with the choices that you're making. Okay, so let's look a little bit at how geophysics and food and dietary choices are related, okay? This is actually a farm, the closest thing to heaven on earth, okay? It's right near my house. And this is what it looks like. You know, when I bike from my home to work, this is the kind of landscape that I traverse. But of course, not all agricultural communities are quite that beautiful. Okay, so here's an interesting example. There's a million dimensions to this problem, and I don't have time to describe them all. I'll just cherry pick a few. Okay, so one of them is this burgeoning field of geophysics called hydrobiogeochemistry. Okay, so it is what it sounds like. It's concatenating 4 different sciences into one. Now, geochemistry, you know, of course, geology and chemistry, that concatenation happened half a century ago. So now we think of it as a discipline, okay? But now, a lot of the reactions that it addresses are mediated by life. So naturally, we appended bio to that. As a prefix. And finally, all of that is done as aqueous chemistry. So hydrology is the next obvious addition. So hydrobiogeochemistry is actually a thing, okay? And it determines the confluence of hydrology, biology, geochemistry of the Earth's surface, okay? Now, farmers do a bunch of things to the surface to have an impact on the rates at which hydrobiogeochemical processes occur, okay? So first of all, they fertilize. That just adds a larger source. Normally, the atmosphere, which is 80% nitrogen, just deposits roughly half dry, half wet nitrogen on the land, or on the ocean, on the surface, and that's what the biosphere has to contend with, okay? Fertilization makes that much larger. Tilling and so on aerate the soil, which is very important because then the percolation of meteoric water, meteoric water means rain or snow, any kind of precipitation, okay? So aeration of the soil basically makes the percolation of this water that much faster into the subsurface. Now, they also do something that's called tiling, not tilling. They do that, and that belongs here, but they do tiling. It's a little known fact, but basically most agricultural provinces, such as the Midwest, have about 6 feet below the surface. It used to be literally tiles. It isn't tiles anymore. It's just perforated plastic pipes. But the purpose of that is basically to keep root systems from being submerged. That's the kiss of death for crops. So whereas it is well known that farmers, let's say, pray for rain, but the minute rain arrives, they become unhappy because now they see the root systems, gradually becoming submerged. That's where tiling comes in, and it totally alters, as I will show you momentarily, the hydrology. And then they also degrade by chemical and physical means the soil biota, and soil biota are extremely important in taking any kind of reactive compound brought down from the surface and processing it and rendering it benign, environmentally benign. So when you degrade soil biota, you basically diminish the ecosystem's ability to render those otherwise dangerous or potentially dangerous compounds harmless. Okay? So all of this, like I said, happens in an aqueous environment. So this is over here discharge, and over here you have days after a rain event. The 0 is when the rain occurs. Okay, and what we're seeing here are the discharge response to rain of two different but otherwise very similar in composition small drainage basins. One is highly impervious, okay? So it's like, you can think about it like pavement, okay? But tiling is very much taking a natural surface and rendering it highly impervious. And the other is natural. And you see that what happens is that the modified one, the modified basin, has an extremely rapid response, and it is equally rapidly decaying once the rain is over. Okay, so you can now picture on the natural environment, the water comes down in a stately manner. It is kind of assimilated into the soil, and the soil biota begins to handle it, etc. And gradually it percolates down, and over maybe a week, order a week, it makes its way downstream. Conversely, in this case, the highly modified one, 12 hours and it's gone. Okay, so because soil biota have a limiting kinetics, in other words, there's only that much that they can handle per unit time. The amount of time that the aqueous solutions are resident over in that soil is extremely important to the soil biota's ability to process that. Well, if you hasten that to such an extent, you basically make that soil biota really unable to handle it, or able very partially. Okay, and the end result you can see right here. This is the mouth of the Mississippi right here, and this is the northern part of the Gulf of Mexico. The contours right here, you see right here, that's bottom water dissolved oxygen in milligrams per liter. Okay, and these are the numerical values. Okay, so the point is natural upper level seawaters will have, let's say, order 10 to 100 in those units. Okay, so these waters are severely depleted in oxygen, essentially just like if you leave a head of lettuce in the fridge and forget about it, it'll decay, decompose, and it'll consume oxygen, because decomposition is the opposite of photosynthesis, so it'll consume oxygen. In the fridge, there's no limitation on oxygen. But in the bottom waters of the Gulf of Mexico, there's only that much oxygen to go around. If you invest all that oxygen in decomposing dead algae, you have none left for the fish. And that's the result are those dead fish that we saw earlier. Another aspect of the choices that the dietary choices I described earlier really is impacting very strongly the radiative balance of this Earth's surface. It's a 0th order attribute of the Earth, the degree to which it receives solar radiation from the star it orbits, that's the sun, and then gets rid of it to space, that's a fundamental attribute of any particular planet. And ours is strongly modified by the presence of agriculture. For example, since we're in North America right now, let's focus on North America. What we're looking at is MODIS data. MODIS is a piece of hardware that NASA put in orbit, and it has cameras looking down on Earth in various wavelengths. And they, in this particular case, you see the degree to which the vegetation, anthropogenic vegetation changes, modified the Earth reflectivity. Okay, so all of the eastern part of the US increased between 2 to 5%. Okay, now that sounds perhaps not that dramatic, but remember that the entire planetary mean of that is something like 30%. 2 to 5% is a very large perturbation, and sure enough, if you ask, what does it correspond to? The fact that I took all of this part of the US, devoted it to crops, and thereby made it that much more reflective to solar radiation, what does that do? Well, here you see it in terms of the net downward surface radiation, and you see that that part is somewhere in the range of 2 to 10 watts per meter squared. That's the currency of global warming, watts per meter squared. So between 2 and 10 watts per meter squared less are warming the eastern part of the US exclusively because of food production. And that is something you can, I know that most of you don't think in watts per meter squared. So let me help you here. The entire anthropogenic perturbation to the planetary heat balance that we have created by, in the long wave part of the spectrum, so-called global warming, is 1.5 watts per meter squared. This is significantly larger than that locally. That 1.5 applies to the planetary mean. This only applies locally, but still, these are large, large provinces. Okay. Another one is greenhouse gas emissions. So in the US, agriculture is about 10% of all emissions. Putting food on our tables is about 25%. So in other words, that 9–10% is roughly doubled or a little more than that with all the things that happen post-production. Packaging, shipping, cooking, all of that stuff. Okay, so that's not enormously important, but every little bit helps. Okay, now agriculture is of course a huge land user. So again, let's focus on the U.S. In the U.S., 47% of the total national surface area is devoted to food production. 48%. Okay, and it's broken down in terms of crops. Corn and hay dominate, and other crops kind of trail this bit to the tune of about 19% of the national surface area. And pasture, range, and forested grazeland, that's 1/3 of the entire national surface area. Okay, and these two together work out to just under half. Now, just to give you a yardstick again, all the things that we actually eat that are enumerated here, that's under 0.5%. That's this green bar right here. So how amazing is that? That all the stuff that we actually eat is like a minuscule fraction of the total, but all of this is basically entirely devoted to animals. Of course, we eat those animals ultimately, but as I'll show you momentarily, it's not a particularly efficient metabolic pathway. Okay? Now, it's important because the environmental costs of diet scale roughly as the land surface used. Okay? So one example is biodiversity. The European, especially in the Netherlands, they care a lot about their songbirds, I guess, and they spent a lot of money trying to preserve on-farm songbirds, only to realize this paper was supposed to be the triumphant enumeration of tax money well spent in saving those birds. Instead, they concluded that all that money, and still 50 to 90% of all species are steadily declining despite all of that hand-holding. Back in North America, it's about 100,000 coyotes that are killed in the name of sparing ranchers the inconvenience called coyotes. 100,000 a year. I mean, try to picture 100,000 dead German shepherds. That's what we're talking about. It's not a pretty sight. Okay? Now, this piece that aired on NPR in 2014 put forth the statistics that ranchers all but wiped out the Mexican gray wolf, the most endangered wolf species in the world in the US. And of course, that is to protect ranching. Okay? Now, one thing that the beef industry is employing exactly the same methodology that ExxonMobil employs and that the Heartland Institute and all of those, this kind of a front series of organizations that are in the business of spewing disinformation. The beef industry is very much in that milieu, and they always tell you, oh, but grazeland out west is a great means by which we further biodiversity. Really? Let's look at that a little bit critically, okay? So here is a paper from PNAS in 2011 that scaled natural rangeland species abundance to be 1, okay? And then they progressed down the gradient of increasing human intervention. And what do they see? By the time you get to moderately used or intensively used, you lost about half of all the species. By the time you got to this, which they unfortunately named man-made grasslands, you lost 70% of all the species. That doesn't look to me like grazing is a great means by which we will further biodiversity in the semi-arid West. And so much so that this paper that came out just a few weeks ago, this guy is the king of something that ecologists call exclusia, which is basically take a landscape, exclude from it all the ungulates, and wait 25 years, come back and write a paper about what happened. And that's what they do, paper after paper after paper. These guys better enjoy, you know, longevity, or else their number of papers is limited. So they just concluded very clearly that biodiversity conservation key is reducing meat consumption. Therefore, it follows that eating land-cheap food is one of the callings of our time. And that is, you know, added to non-geophysical issues raised by food production. For example, this is from the Times just the other day, okay, a couple weeks ago, showing how in the Salinas Valley in California, just southeast of Santa Cruz, you have all of this production of broccoli and arugula and all of that great green stuff everywhere except on the table of those who actually farm these fields. They can't afford that, okay? So that's not really my department. I do geophysics, but I'm certainly acutely aware of and mindful of these aspects, okay? So now it's time to define my work. This is, by the way, our forest, the backyard of our house, and here I am beginning to prepare firewood for the winter. I I come from geophysics. That's where I'm comfortable, and this is what I know best, okay? Climate, meteorology, land-atmosphere interactions. This I wouldn't call myself an expert on, but I use it, okay? That's my comfort zone. Now, there's the societal issues. I will definitely not manufacture new information, new knowledge in this. I will just be aware of what's going on, okay? Agricultural tax and water policies, farm wages and conditions, immigration, etc. Everything that affects farming, okay? Crop sciences, extremely important, okay? What can be, I am condensing crop sciences to a simple two-question synopsis. What can be grown where and at what cost? Hugely important for my work. Nutritional science, again, a whole body of centuries-old discipline that I condense into what extends or shortens healthy lives. And culture, you know, cuisines, preferences, all of that stuff that, you know, that impact our dietary choices. So my work really conflates all of those things. And the way it does that is formally, not by hand-waving, but formally. This is the objective: devise diets and agricultural policies that simultaneously minimize environmental impacts and maximize health outcomes. Okay, that's the idea. And the actual when I say a solution, I mean a vector comprising x1 grams of eggplant, x2 grams of lentils, blah, 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 like that. All of those masses of individual foods that, you know, they can only be positive and real, so that's what this is saying. Finding a solution like that, that's what I do. But it is subject to these conditions, okay? It must minimize a cost function. This is the linear term, which is very simple. It's just, suppose my cost is greenhouse gas emissions. Okay, so eggplant emit that much and squash emits that much. I sum them up, and that's this term right here. Some other things are better described quadratically, and this is what is shown here. It's not really super important. The point is that it's an optimization problem, minimizing the cost, however defined, okay? And you can add to this, I mean, typically in a real problem, you will have numerous terms, not just one. You will have multiple linear terms and numerous quadratic terms in the most general cases. This basically says that this diet must satisfy a series of constraints, as I will show you momentarily. And of course, everything has to be positive, semi-definite. You can't have a negative amount of pork, let's say, okay? So let me give you a kind of a heuristic explanation in the simplest possible way what's going on. Suppose I want to devise a diet that cares about two things. Not exceeding that amount of fat, so this is maximum fat, okay, and this axis here is grams of fat in the diet, and not going below minimum amount of protein shown by the vertical dashed line, okay? As long as I'm in this quadrant, all is well. I have more protein than the minimum, I have less fat than the maximum, I'm good to go, okay? Suppose I'm trying to do that with two foods, okay? Let's start with tofu, always a good idea, okay? And what is shown right here, this is the arrow of increasing mass of tofu, but because tofu has more protein than fat, it's kind of oblique. It adds little fat while adding a whole lot of protein. However, there is a third dimension to this problem, kind of emanating from the board toward you, and that is mass. You can't expect a gal to sit down and put away 2 pounds of tofu in one sitting, okay? So think about this as just lurking above this surface, the glass ceiling that Hillary almost shattered, okay? Now we realize that by the time we hit the ceiling, we're still short of the feasible region. In other words, we maxed out on the amount of tofu permitted, and we are not in the feasible space yet. Not good, not good. But avocado to the rescue. So, so here we are. We add now avocado. We back off a little bit. So you see that this arrow is a little shorter than this, so as to go down relative to the glass ceiling and allow the avocado some mass to work with, okay? And just by simple kind of high school vector addition, we get to, with the ample amount of avocado, we get inside the feasible region. But you see that I can be anywhere between this line and this. So the problem is underdetermined. The indeterminacy is exactly my chance to minimize or maximize whatever the hell I want, okay? So for example, you see the shading, as this is showing right here, is simply monetary cost. Obviously, the more tofu I buy, the more I'll pay, right? So the shading gets darker as you go to the upper right. Now, as soon as we added avocado, now the cost field is bent that way, because now it's avocado that is calling the shots, okay? But it's still doing the same thing. And if I were to simply minimize monetary cost, this will be my solution right here. There is a beautiful theorem that tells us the solution is always on one of the vertices. So we need not look in the entire space. We only need to go vertex after vertex, and we're good to go, okay? Now, on the other hand, if monetary cost was not the only thing, but suppose, for example, we wanted to maximize intake of some protective fatty acid, of which avocado provides a whole lot of, then we would want to have as much avocado as possible, so we will actually be here. Because if we can't go any further than this, because then we will have too much fat. But we can be there, and that will maximize the intake of that protective fatty acid. That's in a nutshell, a highly truncated, simplified version of the kind of optimization problems that I'm discussing. Okay? Now, here's the personal bit, okay? And I get asked this a million times a week. Now is a good time to answer it. I always shrug my shoulders, but today I think I'm going to answer it. So let me show you this. This is my father right there, and he was a seaman. I mean, when I was born, he was a mate, and then he became a captain. And here he is leading our ship into the Corinth Canal, separating Greece proper from the Peloponnese, okay? And when he met my mother and they became an item, and shortly thereafter my sister and I came along, we kept on sailing, and this is how I grew up, on ships. I never went to school to speak of, except whatever my mother kind of squeezed in between storms. And that's what it looked like, okay? Now, when I had this particular spot on the right side of the bridge, on ships they call it the starboard side, and that's where I would sit and worry if we're going to make it up the next wave or not. It was a great childhood, and it took us to all kinds of nice places. This is Western Africa. We spent the better part of a year there and met somebody smaller than us, which was uncharacteristic. But when my sister was 18 and she had to go to the military, I really didn't want to continue doing that by myself. just with my parents. And so both my parents were born in kibbutzim, and they continued sailing. I basically struck it on my own. I was 13, and I went to live in this kibbutz. And that's when I first started, when I first met cattle. And it was love at first sight. And I still very much love cows very much, okay? So this was dairy. And you see, in '76, I went to the military. Then I biked around the world for several years, all kinds of good stuff. But then I came back to Israel. In '82, there was a war. That's what brought me there, to reserve service. But then after that, I stayed. And I said, well, what is it that I want to do? Really, cattle is what I love best. Let me raise cattle. So the mothers were living in the Golan Heights, you see right here. They would give birth to calves. They were all synchronized. All the mothers are synchronized. So it's based on the availability of grass. So they would all give birth to a calf, sometimes two, between late September and early November, when the grass is actually green and what this bleak, not this bleak yellow that it now is. And then they would be brought over here to this place called Kfar Yoshua, and that's where they would gain about a kilogram, sometimes 1.5 kilograms per day, eating like that, okay? During that time, I availed myself of something that Israel, because of its socialist past, had, which was a free, you can think about this essentially like an undergraduate major from Cornell in animal science, okay? But it's not academic. It's meant for herd managers, and that is what I suppose I was at that time. And I started and graduated that in this, it kind of looks like a kibbutz, really, but it's sort of a pseudo-academic place. And it was extremely rigorous and very, very wonderful. And finally, then as Judy said, then I switched to math and physics. I liked it, etc. And then I started a PhD. This guy, Mark Kane, is my thesis advisor. He's a professor of applied math at Columbia and now a good friend. Okay, so here's the answer. That's the end of the aside. Okay. So how do you get there? Well, I think that maybe early life dominated by ocean, atmosphere, and cattle. Having no K-12 schooling always helps, I think. You know, so basically, if you learn anything, it's not because your teachers nag you, but it's because you saw something and you want to understand what the heck is going on. That's a very good motivation, at least in my experience. And then once I stopped being a bum and became, you know, serious, I enjoyed really superb training, both courtesy of the Israeli Ministry of Ag and then in geophysics with Mark Kane. And then I was a postdoc actually across the common at the Department of Earth and Planetary Physics. Then it was called Earth and Planetary Physics. So it sort of makes sense. I don't know. If it doesn't to you, oh well, what can I say? Okay, let's do some homework here, okay? So this is a paper in which we took the mean American diet, which comprises, it has 3,800 kilocalories per person per day, that much from plants, and all the rest is from animals, okay? And we asked, what happens if those calories, about 1,000 calories a day from animal sources, what if it obeys a certain pattern, for example, lacto-ovo-vegetarian, or purely red meat diet, or some only poultry, etc. The diets ended up stacking up like this. Vegan was the least greenhouse gas intensive. Red meat was the most. MAD is, I'm very proud of this, it's the mean American diet. Very aptly acronymed. And this was taken up by pretty much every news outlet in existence. It was my first introduction to the sort of the madhouse that science coverage in the media is. But this is the upshot. If you take two Americans eating the same number of calories and the same quality of diet, but one only from plants and the other like the mean American diet, the difference between those two is 1,500 kilograms of CO2 emitted per person per year, excuse me. Now, being that each one of us now is responsible for 21 metric tons per year, that's 7% of the total that can be eliminated by switching from the MAD to plant-based diet, and that's maybe why it caught the attention of those media outlets. If you recall, that 7% is the lion's share of what I showed you earlier, the 9%. Remember the 9%? It's this, okay? This. So almost all of it, let me speed this up a little bit. Almost all of this can actually be eliminated by that dietary transition. Well, that was pretty interesting, okay? But then I realized that, well, I mean, if you're looking at something that's at most 9%, that's not really that interesting. Let's look at something that actually dominates, okay? And that is land use over here, and reactive nitrogen, NR is reactive nitrogen. Think about this as contributions to water pollution, okay? So here, this is something called a Monte Carlo solution, which means you kind of randomly envision people eating in various idiosyncratic ways, okay? And there are 2,000 people eating the mixed diets like the mean American diet, and 2,000 people eating plant-based diets. Never mind the difference between those. That's optimization or no optimization. It's not really supremely important, okay? What is important is that we devise 4,000 diets, half mixed, half pure plant, and we see now the difference in terms of over here in the vertical, the contribution to water pollution, and over here the contribution to demand for land, cropland, and we see the national scale difference between those two. And by the way, there is nothing in the way the problem is posed that will make these clouds and these clouds mutually exclusive, non-overlapping. They could have overlapped if they so chose, but they chose not to. And that is because of the stark difference in land consumption and in contributions to water pollution. So here's the upshot. In terms of land, in terms of, land, which is this distance right here, okay, you save something like 130 million acres. National cropland is just over 400. So that's somewhere between a quarter and a third of the total is saved by this, these choices. Now, in terms of contributions to water pollution, you save 7 million metric tons out of a total national of 11. Again, a very significant difference. Now, let me speed up here because we don't have that much time left. So let me just introduce you to this guy who I've been working with for a number of years now. Who, you know, it's really an honor almost comparable to the honor that I feel being part of the Radcliffe crew. But let me take you to the paper that we're about to submit, and I'll wrap this up because I'm running out of time. Okay, so if you think switching from whatever you're eating now to plants is very hard, this calculation asks, what happens if we only replace beef? Okay, beef contributes only about 65 grams per person per day. That's it. But it claims, depending on the resource that you're looking at, 80 or 90% of the total national. So it contributes almost nothing, and it uses almost everything. Now, so for example, here, if you just switch from beef to poultry, okay, this is the amount of concentrated feed and processed roughage and pasture that are going into beef. This we treat as entirely free, okay? So not contributing anything because chickens can't graze, okay? They are monogastric. So this is just free, and these two, if you reallocate them to producing poultry, you will be able to increase the output calories fivefold. 520% more calories will be available if you just made that simple switch from beef to poultry. And how many, check this out, how many more Americans will be fully sustained on that addition? 116 million out of a 320 million nation. Okay? Now, this is in energy. What about in protein? You will have fourfold more output protein in this substitution. Look at how much smaller the losses are. This red is the loss in the beef route. This one. This is the lost protein in the poultry route, and it's, of course, dramatically smaller, and it will add 140 million additional Americans. When you look at results like that, you say, really? You have to eat beef no matter those 140 additional million Americans that could have been sustained on the same resources just because you think that beef is indispensable? That just doesn't make sense. This paper refutes a commonly repeated but never correct assertion that grass-fed beef is somehow superior. I will skip that. And finally, this paper is now working its way through review. The way we put it, nature has not yet rejected it, okay? So, this is what we're saying. We're asking, okay, people, you want your beef, fine. You want sustainable beef, how much can we have? Okay, so but of course, what is sustainable beef? No two Jane and John will define it similarly, and I don't claim that our definition is by no means unique or definitive. But here's how we defined it. We said there are two things that beef currently eat that really have no alternative use, and that is industrial byproduct and pasture. No other, well, I mean, lamb can graze, but that's a minuscule amount, so forget lamb, okay? So, but other than lamb, it's cattle, okay? So fine, let's allocate the entire pasture land currently used for beef, still for beef, and all the byproducts. You know what I mean by byproducts? For example, you squeeze citrus for orange juice, the peel that's left is very high quality cattle feed. Okay, so that's an industrial byproduct. Mills, you know, you make flour. It's the results, well, other than the flour that we claim, all the other is very high quality cattle feed. Okay, so we allocate all the byproducts currently used for beef, still for beef, and that's shown right here. I'll explain this in a minute. And increasing fraction of the total current pasture land used, okay? So this left hand means no grazing at all, only byproducts. This means the full 670 million acres currently grazed by beef, still grazed by beef, okay? And this is the percent of today's beef supply we can have with those conditions, okay? Byproducts alone only give us something under 5%, almost nothing, okay? But then when you start adding pasture land and you get to some non-vanishingly small amounts. By the time you get to, let's say, half, you get to over here, it's somewhere like 35%. If you go from half of the pasture land to full, remember, this is a vast area. Going from half to full is an enormously large area, 300 million acres of land, okay? You only go from 35% to 39%. That's it. So it really seems like if in a sensible kind of resource allocation, you will say, you know what, let me be somewhere around here, claim the prime pasture land for beef, fine, let's do that. But let's not eke out every last morsel of pasture at great environmental cost, for example, to riparian buffers out west or whatever, all the things that grazing cattle does so much damage to, okay? And you get oodles more of nutrients. For example, right here, this is alternative protein deliveries. So for example, if you take the 93 million acres of fine, high-quality cropland, forget pasture land, that's we gave to the beef, but only high-quality cropland that is currently used for feed for beef, and you plant in it, let's say, wheat or spelt, how much more protein will you get? Well, you will get somewhere around 9 times the supply of protein beef currently delivers. 9 times, okay? And what about nutrition? Let's skip. This is the environmental savings, and they are enormous, okay? But let's look, I don't know, let's pick one, soluble fiber, okay? Look at this. What this means, for example, is if I took those 93 million acres and planted them soybeans end to end, I will have gotten for each one of us 4.5 times the additional soluble fiber than the entire soluble fiber delivery by your entire diet. That's what it means. And it goes on and on in terms of protective nutrients. I don't want to beat a dead horse, so let's just get to the crux of it, and I'll let you go. Okay? So here we go. Eating, and now I'm going to do something that scientists do not do, and that is I'm actually going to read, okay? Eating is a personal, cultural, culinary, social act. That we all know, okay? We also know that it determines your health span as powerfully as genetics or exercise or whatever, okay? My work adds a dimension to this, showing that in making dietary choices, you get to tip the scale of environmental, social, and political contests that right now, good luck if you think we can tip any of those scales, okay? For example, who wins? A hay farmer enabling growing Chinese panache for beef, that's an allusion to the Klamath Basin, or salmon that depend on these contested waters and the native populations that depend on them. Who wins, a Mississippi shrimper or the Iowa farmer whose nitrogen-rich effluent kills her catch? It's our choice. Is what's on your plate furthering your health or that of Archer Daniels? Again, that's our choice. Importantly, health, environmental, and societal considerations often, but not always, lead in similar directions. It gets hairy. I'll grant you that. All right, thanks much.